Okay, good morning, everybody again. A very warm welcome to this two-day session on the 5G cellular communications landscape. I'm Sheila Prabhakar. I head the Wired and Wireless Technologies Center of Excellence here in Art Park. For those who are new, Art Park stands for AI and Robotics Technology Park. This is an incubation hub promoted by Indian Institute of Science. Art Park head office is located within IISc premises, and we have a bigger facility that we call as Art Garage. That is about 5-6 kilometers from Indian Institute of Science towards northern part of Bangalore in HMT layout. We call this facility Art Garage. Many of the startups incubated here operate from Art Garage. And the Wired and Wireless Technology Center of Excellence is a program within Art Park. And all activities of this COE are also held here in Art Garage. This COE is Government of Karnataka funded activity, and it started in this financial year. This picture symbolically represents the charter for the WWT COE. Our main charter is to foster innovative market-ready solutions. How we achieve this is, on one hand, we interface with research and academia to get access to deep tech communications and AI technologies. We work with innovators and startups who actually develop these market-ready solutions. And to ensure these market-ready solutions have a societal scale impact, we work very closely with industries, industry bodies, and industry associations. So in summary, our stakeholders are research and academia, innovators and startups, and industries. Is a representation of the 5G test bed that we have here at Art Garage. We have two parallel test beds. The first one we see on the left side is Bharat 5G test bed. This is one of the 100 test beds that is set up by the Department of Telecom. And on the right side, we have a parallel open 5G.
The slides are not.
As you can see here, we have a combination of commercial systems, open source solutions, monolithic G node Bs, split G node Bs, all combinations available in the setup here. While the Bharat 5G lab setup is more amenable for verification of test cases, use cases, and carrying out the testing of the solutions, the parallel open 5G test bed is more friendly for carrying out experimentations on solutions developed for the infrastructure. The facility is for testing and demonstrating innovations. The facility is available to the innovation community, the startups, the academia, and the industry. Industry partners can also make their technologies available through this facility. A brief overview on some of the research and innovation programs that we carry out here. Earlier this year, when we started the activities, we sent out a call for proposals for research and innovation programs. The selected programs are listed here. We got proposals from academic institutions across Karnataka and even outside. The 7 programs shortlisted here are a combination of research and innovation programs. The research programs essentially result in generating white papers, technical reports, publications, and patents, while the innovation programs develop technology that is useful for technology licensing, or it can be used to spawn a startup, or even it can be open source, depending on the case to case. Okay. Yeah. There are some in-house technology demonstration programs that we are doing. 3 of them are listed here. All of them are 5G enabled technology demonstration programs. The first one is the Drone Corridors program. We are working with multiple startups here. Two of the drone companies, one is a private 5G infrastructure development company, and then the third one is the UTM software company. These are all in their early stages. We are working very closely with them. We are also working with some of our industry partners in carrying out field trials for these drone corridors. Then the second one is related to the factory digital twin. Again, we use the 5G infrastructure here, the capabilities of the 5G in terms of the volume handling, the bandwidth, the latency, etc., are very well exploited in this demonstration of this particular use case. Then the third one, what we call as the driver assist. Here our objective is to, we all know the ADAS solution. Many of the big automotive OEMs have invested heavily in ADAS solutions. What we are trying to achieve through this program in-house is to democratize ADAS and adapt it for Indian traffic conditions, especially keeping the two-wheel drivers in mind. So this is the third program. Again, this exploits the advantages of 5G cellular communication. Some other activities, we are exploring how 5G technology can be used for the positioning. This has multiple use cases. We'll talk about it in the next 2 days under different headings. Then iOS MCN is another program. This is the India open source program for mobile communication network. We have one session tomorrow about this. Our objective here in Art Garage is to take iOS MCN releases and make it available as part of our testbed so that all use cases and the testing that happens here happen on the iOS MCN. Then skilling is another important activity that is part of our Center of Excellence here. This is about the today and tomorrow sessions that we have planned. And then we have also planned a long-term certificate course on practical 5G. This has 3 categories, the basic, intermediate, and advanced. This is a very extended program. And both oriented for theory and it's theory and comprises of theory and practical sessions, both distributed equally. We will soon be making announcement for this on the dates and other details. Just a snapshot of the industry partners with whom we collaborate on a day-to-day basis. Several of them, we are working very closely in some of the technology demonstration programs that I mentioned in the earlier slides. This is a brief overview of the activities of Center of Excellence here. I'll give a overview of the 2-day session that we have.
Please fix the slides. We can't see your
2 days, today and tomorrow, I would generally split it into 5 categories. The first one, we'll have the inaugural address by Professor Anurag Kumar. Then the next is a technical overview session, session number 3 and 4, a technical overview on 3GPP and the 5G cellular communication. Then the third category, I would say, it is about, we have a talk by Mr. Saurabh Mittal from Bharti Airtel. Our intention here is to get an overview of the cellular communication deployment status in India. The current status, the future plan, what are the challenges, what are the use cases that are popularly being used on the 5G network today. The fourth category are mostly the industry talks here. We are having industry talks by many of our industry partners. As you can see, the Nokia, Leica Wireless, Signaltron on the first day. Here, the intention is for our partners to share with the audience the solutions that are available today, the offerings they have, what are the future plans, and what are the opportunities and challenges in deploying these infrastructure solutions. In the second day, we continue these industry talks, and we have our partners from neural networks, Resonance Technologies, giving those talks tomorrow. And then the last sessions, I would say, are here what are listed as serial number 3 and 5. Are more about, they talk about the use cases. The first one is by Mr. Vinod James from Qualcomm, serial number 3. Serial number 5 is by Dr. Abhijit Leele from Art Park. Both these sessions are oriented towards the use cases that are possible to be realized on 5G. Then the serial number 4 again is classified as industry talk. This is on the iOS MCN, the India Open Source for Mobile Communication Network. This activities which is taking place in IASC. We will have a session on that, and the audience can get to know how this iOS open source India Open Source program can help in building the 5G solutions. So this is an overview. Yeah. Now we will move to the inaugural address by Professor Anurag Kumar. And just to give an introduction about Professor Anurag Kumar. Professor Anurag Kumar is currently the honorary professor at IAC and is the former director. For people from academia, need no introduction about Professor, as he has been the authority on the topic of communication networks for decades. He's not only a great academician, but also has made tremendous contribution to the telecommunication industry. After graduating from IIT Kanpur and doing his doctorate at Cornell University, Professor has spent his early years of professional career at the prestigious AT&T Bell Labs as Master of Technical Staff before taking a faculty position at another prestigious institute, that is Indian Institute of Science. He was one of the leaders of the EarNet project that established India's first nationwide internet. He is widely consulted by government and private organizations and has mentored networking startups from early years to a global footprint. He's the author of 2 major technical books which are widely used around the world. He has published more than 200 papers in journals and conferences. Awards and recognitions to his credit are innumerable. Just made an attempt to list them here. We are extremely privileged and honored to have Professor Anurag Kumar deliver the inaugural address for this workshop today. Thank you very much, sir, for your time and willing to share your wisdom with us. Thank you very much. Once again, a very warm welcome to all the participants. And now I would like to hand over the session to Professor Anurag. Thank you.
Thank you, Sheila, and thank you for inviting me here. Thank you very much. This is a skilling workshop. I would use the opportunity to maybe convey some high-level common information from the skilling point of view, and I'll also convey some information about the work that we are doing under what we call the Cocoa Vineyards project, which is being funded by Art Garage, which Sheila Prabhakar described to you at some length. Cocoa Wirenet stands for Control of and Control Over Wireless Networks. Being a center of excellence in wireless technology, this is one of the areas we have chosen. And I'll explain to you over the next few slides. Perhaps you'll get a feeling for what that term means. My main topic is high performance private wireless networking. I guess much of what we hear about 5G from operators and from manufacturers and developers is about public 5G. Given the emphasis of Art Garage towards industrial wireless, the emphasis here is going to be more on private wireless networking. And the term CPS I'll explain briefly in the next slide. And the industrial, of course, is familiar to everybody. So if we look at the area of CPS, which is a short form for cyber physical systems, quickly let me illustrate what that means. So in the middle is what is familiar to the audience here, which is so this area of CPS comprises essentially three technologies. Of course, there's a physical domain, which we're concerned about in designing the CPS for. Could be a civil structure, farm, factory, mine, or whatever. On top of that, the next layer is the Internet of Things, sensors and actuators, and communication networks, which is the topic of this seminar. And finally, very importantly, what are CPSs used for? They're used for inference, decision-making, and control. That is the ultimate goal of CPSs. It's not IoT. It is the ultimate goal is the inference, decision-making, and control. Now, CPSs have existed for a very long time, as far back in the 1970s, when Bosch company introduced microprocessors in fuel injectors. But the CPS area was given a thrust in 2006 when the US NSF, National Science Foundation, created a white paper by Helen Gill and Rajendra Baheti, which launched the area of CPS around the world. And we have been following that area for a few years in India as well. Now, what differentiates modern CPS from what Bosch did 50 years back? What differentiates modern CPS is that, first of all, the CPS system is loosely coupled. So wireless networking is key to be able to build a CPS for modern requirements. And of course, at scale. So for example, an entire large factory, a water distribution network, or a railway track safety, very important for us in India. Moving on to the next section of my talk. So this talk is going to be about 5G and Wi-Fi, high performance networking for the industry. So what does the industry need? So you look at this diagram here taken from the paper reference at the bottom. So one typical situation will be, there will be an edge device, an edge computer. There will be several factory machines, like this robot that is shown out here, various ground vehicles, and you have these access points, which could be 5G base station, G Node Bs, or there could be Wi-Fi access points. And the entire factory is wirelessly networked. The edge server, the edge machine, is controlling the production robot. It orchestrates the transport robots. All the sensing and communication and control information is flowing over the wireless network. And the important aspect of running a factory on wireless networks is that you have to contend with random data losses, contend with random delays, and out-of-sequence packet delivery. So is it possible for a factory to be run over a wireless network, where the wireless network has all the deficiencies? And secondly, is it possible to design the wireless network in a way that the deficiencies are minimized, with data losses, delays, and out-of-sequence delivery? My topic today, although our research topic for Art Garage is to do both, the topic for today is the second one, that can we shape wireless networks like 5G and Wi-Fi to be able to provide the kind of quality of service required in a factory setting. So the overall system is expected to work correctly, just as it works on field bus or any of the wireline technologies, Ethernet, that would be available today. That's the problem. So towards this, if you look at the evolution of the 3GPP standards, you will see that in 2022, just about 2 years back, 3GPP has actually come up with various quality of service profiles. These are not the 5 QIs which they defined many years back. These are actually specific profiles which are application oriented. Because the table is large and it is difficult to read, I'm going to go over one row. This row, the row that is highlighted in that red box. You see that I'll focus on the performance profile. So this column is regarding end-to-end latency. End-to-end latency should be around 10 to 100 milliseconds. That's the latency bound. The service rate is about 10 kilobits per second. It's a very low bit rate application. The application we're talking about is basically a mobile operation panel. That is, there's a panel in the factory connected to the machines via wireless, and still you want to be able to keep the dashboard and the operation commands over wireless. So 10 to 100 bytes are the message sizes. 10 millisecond, 100 millisecond are the transfer interval. That is the rate at which the packets are being sent to the mobile panel, the operation panel. This is very important. The service interval, the survival time is a transfer interval. What that means is, how long can the application survive before it fails? Well, the application can survive for a time of about 10 to 100 milliseconds. So this is how 3GPP is defining the latency that can be expected. How long you can delay a packet up to the maximum. The device is stationary, and so on and so forth. So these are various examples of, in a factory environment, what sort of application performance can be expected. And the mobile wireless network should be able to support that application performance. Now, I was hoping to be able to do full screen, but I suppose we have to satisfy ourselves with what we have today. Now, this is a very interesting table taken from a paper which I've referenced on the top here, Orton and all from 2021. It's a comparison between the 5G and the Wi-Fi technologies, okay? You will see certain rows highlighted in red and green, but the rows that are not highlighted, what it means to say is that 5G and Wi-Fi are fairly comparable. The maximum bit rate is 2 Gbps or 1 Gbps, downlink and uplink. Wi-Fi is 10 Gbps and beyond, actually. So if you look at this part of my bullet points out here, Wi-Fi 7 offers 23 Gbps at the peak rate. Many other features, the physical layer features, OFDMA, and so on and so forth, are pretty comparable between Wi-Fi. The physical layer of Wi-Fi and the physical layer of 5G are very comparable. What are not comparable are things that are highlighted in, okay, and let's look at the cost, the business model and cost, the user equipment prices, the chip prices, the installation and skill level required, and the development skill required for 5G are very high at present. For Wi-Fi are very low. Look at the greens of 5G. 5G is a centrally controlled system, and 5G is centrally controlled and managed, whereas Wi-Fi is mainly uncontrolled or it is decentralized. Okay, so let's go here. One of the important things to understand from a skilling point of view to this community is this: that simply because you have a high quality physical layer, simply because you have synchronization between the base stations, doesn't guarantee any service to any application. Ultimately, the quality of service that different applications require are guaranteed only by scheduling. You have to do scheduling at the base station level, scheduling across base station, you do interference management. Only then can we give the quality of service required to the applications. So the physical layer being very high quality, that doesn't guarantee you can give quality of service that is required. It's another layer of functionality on top. So 5G is centrally scheduled. It is predictable. It can reduce congestion because of central control. You can manage interference, and you can eliminate collisions. On the other hand, Wi-Fi distributed control, the airtime allocation is by random access, there's no interference management, and is primarily what is called best effort quality of service. And even that is suboptimal due to the channel access being uncoordinated. I should say being uncoordinated. On the other hand, 5G has high equipment cost, installation cost, and operations cost. Indoor Wi-Fi has been around with us for a couple of decades, and it's evolving every 2-3 years. We are currently in the Wi-Fi 8 generation. You'll soon see Wi-Fi 8 next year. Wi-Fi 7 is being rolled out this year. There are 3 billion Wi-Fi enabled devices shipped annually. So there is a huge difference in the scale at which Wi-Fi is already available and Wi-Fi is deployed. Many factories would already have Wi-Fi deployed in their systems. And the question that I will begin to ask, and this is a research question that we are doing have done and we are doing for our garage, is it possible to shape Wi-Fi to be able to provide the kind of industrial quality of service profiles? One example you saw a couple of slides back. Okay, so I'll demonstrate to you quickly. Without telling you what we have done, I'm going to show you what the result of what we have done is. It's called an overlaid central controller. Central control is important. I'm going to show you results from this simple test bed in our EC department building. There's an access point here. There's an access point here. All the wall, the granite, thick granite walls. There's a station here. There's a station here. I hope my pointer is visible. There are 2 stations in between. And this is the key problem that Wi-Fi faces. This station gets interference from this access point, and this station gets interference from this access point. This is what you call cell edge UEs in the cellular world. Okay, so how do things behave if you do this in a Wi-Fi setting? Well, here are some experimental results. All of these experimental results. I show you on top, on the top left, a Wi-Fi network like what I just showed you earlier. 2 access points, 2 stations associated with this AP, it's like 2 machines, and 2 access points out here. You'll see this thin, faint line from this AP to this station, and from this AP to this station, which indicates interference. So if you activate, for example, this AP, and at the same time this AP, then to this station, then this station will receive signals from here, but interference from here. What happens when that happens, and how do you fix that is what I'm going to talk about here. If each of these machines or laptops was all by themselves, you get very high throughputs, 108 Mbps to laptop 1, 94 Mbps to laptop 2, 97, 126 Mbps are the rates available to the 4 laptops going from left to right. Operate them all together and see what happens. The laptops in the middle get 2.9 to 7.45, very poor throughputs. Okay, you deploy what we have done. You actually coordinate the access points in a certain manner, which I won't spend time on. I don't have that time. And you see what throughputs go up. The throughput 2.9 becomes 21, 7.4 becomes 21, 61 goes to 49, 69 goes to 50, because there is time sharing across these different co-channel devices. Okay. The last row out here talks about the optimal performance versus what we are able to achieve. I won't spend time on that. We are very close to optimal. So this is what we can do for downlink bulk transfers of data. For example, downloading the programs into CNC machines. What about uplink? Okay, uplink could be some information being sent uplink from machines or computers to the internet. Again, if you run the 4 machines together, uplink, you see the middle, a very poor performance, 0.0 Mbps, 0.045 Mbps, 0.037 Mbps, very poor performance. With our technique, 17 Mbps, 33 and 34 Mbps, much, much better. I can say more about it in terms of the columns that I have at the right, but I don't have time, so I won't talk about it. Very close to optimal, as the last row shows. So both downlink bulk transfers and uplink transfers we can handle extremely well. What about video? What about real time? So in this picture, we are demonstrating that there are two access points, downlink transfers to this machine, this station, downlink transfers to this station, along with a video. There's a video out here. If the video was all alone, it would get 1.6 Mbps as shown on the top, and jitter of only 50 milliseconds as shown on the right. You put these 2 bulk transfers together with the video. So the video is going, and you're simultaneously doing downloads into some machines. The video bitrate falls to only 50 kbps, and the jitter goes to about 3 seconds. Very poor performance. It clearly shows that because of interference from here to here, interference from here to here, the default Wi-Fi is unable to manage the network. The video performance goes for a toss. You bring in the technology that we have developed, that we are doing research on, and you see what happens. The 2 TCP transfers are still going on. The video is coming. The video bitrate is back to what it should be, 1.6 Mbps. The jitter is down to what it should be, 50 milliseconds. Not only that, the TCP performance went from 23.8 Mbps to 24 Mbps to 38 and 36 Mbps. So not only has the technology helped TCP perform better in the face of interference, but it has made the video perform better. And I have videos out here to show you, but unfortunately, because of not going full screen, I can't show the video comparison between the left-hand side with our technology and left without the coordination between the access points. One more example, maybe I'll skip this example, I'll go to the last example. This is a very typical factory application where machines are sending real-time data uplink. Okay? For example, like that panel that I showed you earlier, the mobile panel. The mobile panel wants to occasionally send some control commands to the machines. Okay, so these control commands are being sent from, say, this panel and from this panel upstream into the Wi-Fi network, and they have to be received by the computer, and the computer does something with that, or maybe it goes to another machine. Okay, now Wi-Fi is extremely poor at handling this kind of performance. Let me show you what happens, this kind of data. Suppose, okay, and there's a bulk transfer. There's a bulk transfer from this computer down into this machine. For example, you're downloading some program, a large program, to a CNC machine. So you're simultaneously downloading a large program to a CNC machine. While uplink, you're sending these very small 50-byte packets occasionally. What happens to those 50-byte packets? Hope you can see my pointer. This is what is called the complementary CDF. The probability that delay is greater than D is on the x-axis and Y is the probability. This blue line here, which is almost touching the y-axis, shows you what happens if Wi-Fi is operating only with these two devices. There is no downlink bulk transfer. But this is what happens if you test Wi-Fi all by itself and you send these occasional packets. Because the Wi-Fi's physical layer being so strong, you get very small delays, about a millisecond or so. In fact, the number is given in 2 milliseconds with a probability of 0.5%. Very good. So that is it meets the requirements. The moment you add this bulk transfer going to another machine to be able to do some kind of bulk program or something, look what happens to this complementary CDF. You get 800 milliseconds, you get 101.2 seconds. With the probability of 1%, you're getting about 500 milliseconds and 600 milliseconds. Suddenly, just the creation of this, addition of this traffic, which is fighting for the airtime, is completely throwing off what Wi-Fi has advertised as being extremely good. Okay. And then if you do what we have done, that is, we coordinate the access points, we are able to eliminate interference, we coordinate the applications, we are able to push this CDF down to this, about 20 milliseconds. It's 18.5 milliseconds with a probability of 0.5%. So you see, just by using default Wi-Fi and coordinating things in a particular way like what we have done, you're able to extract the performance which the factory would require. So the question is, here's the point I'm trying to make. Wi-Fi is widely deployed. Wi-Fi has a high quality physical layer. Can we shape it in a way that we can actually achieve the application performance that most application factories would require? And the answer that we have given is we can, if we work at it. Okay. Let's move on to 5G. Since this course is primarily on 5G, I'll take another 5 minutes. Now, as I already mentioned in the beginning, that 5G by itself, the raw physical layer, the TTIs, half millisecond TTIs, the synchronization across the base station, none of that is going to be useful unless we build on top of that a control mechanism. And those control mechanisms are embedded in base stations, the schedulers. There are various controls which are there across base stations. There's the non-real-time RAN interface controller and many such things. Okay, unless that coordination is done, the handover controls, unless coordination is done properly, even a very high-quality physical layer, highly synchronized, will not work well. Let me give you an example of what of what we have done to demonstrate. Further, I mean, of course, a lot of work has already happened on scheduling in 5G. I'm showing you what even better scheduling can do. Now, those of you who are familiar with 5G technology, 5G terminology, would know this concept of a TTI. So these are half millisecond TTIs, during which there is the OFDMA grid out here, into which we are stuffing data to be sent from the base station down to the UE. One important issue is that when we stuff data into these TTIs, the data can be lost on the way from the base station down to the UE. If the data is lost, it has to be retransmitted. One important feature in these base stations, at least the one that we are working with, called the OAI sort of software-based base stations, is that they will prioritize retransmissions. So if you lose some data, you will send the lost data first. Only then do you schedule new data. Okay, so only if there is no retransmission scheduled is the scheduling opportunity for sending new data. Okay, now the schedulers that are there typically, even in the good base stations, do not account for that. They don't account for the fact that if you have to schedule something, you should account for the fact that this packet can be lost, this transfer block can be lost. Are we able to account for the fact that you can lose something? Well, we have designed or we have modified the existing schedulers to be able to account for that. I'm going to show you the impact of that rather than tell you what we have done. This is what is called the rate region. So suppose there are two UEs on the ground This is also indoor, so the two UVs a few meters away from the base station, UV0 and UV1. Okay, this is a part of my skilling message. One very important concept that is there in wireless, particularly in wireless, is the notion of a rate region. What does this purple or this pinkish line shows is that between these two UVs, you can only achieve rates which are within this triangular, roughly triangular area. You can achieve no rate outside. I cannot expect to get 250 Mbps and 80 Mbps for this UV pair, but we can expect to get 150 Mbps and 40 Mbps. An important concept that anybody working in wireless should be familiar with. Now, if we go, so this pink line that I've shown is the rate region that you get if you ignore the fact that when you schedule something that can be lost. Okay, if you account for the facts that what we schedule can possibly be lost, we get a bigger rate region. A bigger rate region means that you can actually achieve all the rates that are on this line rather than only on this line. Now, it may seem that the improvement we've got is rather small, but let me show you on the right-hand side. Those who are in communication will understand this very well. Then a 5% increase, which is actually giving you that. A 5% increase in system throughput corresponds to a 1.5 dB increase in SNR. But those who are in the operational area would know that a 1.5 dB in SNR is a very large increase in dB. You have to do a lot of work at the physical layer. You have to do a lot of work with the link budgets to be able to get a 1.5 dB SNR improvement. And here we are able to get that SNR, that the effect of 1.5 dB SNR improvement only by designing the schedulers more carefully. So the message only is this, from a skilling point of view, is that what you do on top of the physical layer can dramatically enable the physical layer. And the physical layer improvements are gradually coming to a saturation point, and perhaps paying attention to scheduling and the control across the network is going to be more important. Okay, this is another example of what we have done. Okay, in network slicing, one of the important requirements is to be able to give a particular UV a guaranteed bit rate, or a bunch of UVs a guaranteed bit rate. We have done that, and it actually works quite well. So these are the same two UVs. We have given a guaranteed bit rate of 200 Mbps to UV1, and the other UV gets whatever it can get. And this UV is moving around the room, and only here, only in this little area here, there is a small glitch because the UV went too far away from the base station. Everywhere else, the UV is getting 200 Mbps, and the other UV must adapt itself. For example, when this UV is close to the base station, the other UV gets a high throughput. When the UV is far from the base station, the other UV gets a low throughput to be able to enable that UV to get 200 Mbps. Okay, I'm almost done. And I think I'll skip this slide. It's too complicated to explain out here. And I'll go to my last slide. I'm also out of time. So in summary, 5G and Wi-Fi technologies both have very powerful file layers. I think this is important to understand, that we cannot discount Wi-Fi, because Wi-Fi has very high quality physical layers. In terms of raw bit rate, they are faster than Wi-Fi, than 5G. But the physical layer themselves are application agnostic. The physical layer does not know what the application is running on it. It is simply like a road carrying vehicles. Okay, it is the control on top which stuffs data into the physical layer and gets you the quality of service you want. So the network controls are essential, such as transmission scheduling over time, frequency, and space, interference management, admission control, mobility management, and handover management. For enabling these powerful file layers to provide a variety of services that would be required to a wirelessly connected modern factory. Now, whereas the operator is only dealing with users who do YouTube and downloads, and that's the maximum they want to do. But if you look at the list of requirements that the factory has, and there are 5 more tables like that in the 3GPP 2022 standards, there's such a list of different requirements in the factory, that how do you shape that 5G or Wi-Fi to give all the requirements that's to be done at the higher layers? Cellular systems have been undergoing 20 to 25 years of work on control and management, which is why their centralized control is so powerful. Wi-Fi, on the other hand, has seen widespread deployment, low equipment, and low deployment costs. But the distributed controls in Wi-Fi, which has evolved over the years to make Wi-Fi more accessible, easy to deploy, and easy to use, has led to poor network performance over good physical layers. Efforts are needed in the community for Wi-Fi technology to reshape itself for the demanding applications, and the standardization efforts up to Wi-Fi 7 do not provide, I emphasize, do not provide the network-wide solution. They can provide solutions for one AP controlling 10 stations. What we really want is network-wide solutions. And our research has actually shown that such controls are possible over Wi-Fi. It's up to the industry now to take these ideas and perhaps use them to the benefit of the factory application. So thank you very much. I'm done.